Okay, so let's go to the second order differential. Yesterday we did the first order differential equation, but that was trivial. I mean, it was just one integral, right? So of course, if the functions a and b are given to you, then you can try to integrate it, okay, and find the solution for the u. But now let's go to the second order differential equation because that's more interesting. Right here. Okay, so the differential equation will be okay. These are given function ax d2u by dx2 plus bx du by dx plus cx u equal to q of x. Okay, this is the linear second order differential equation, but it's inhomogeneous if q is not 0, right? So it's inhomogeneous linear second order differential equation. Okay. Right. So, but as I said last time, that in order to find the solution of this thing, it's useful to first look at the homogeneous ones. So the homogeneous just is obtained by taking the right hand side equal to 0. So the left hand side is the same, just put the right hand side equal to 0. So that's a homogeneous linear second order differential equation. So in this case, we know that the space of solutions will be a vector space, right? Because if you are given u1 and u2, two solutions which are solutions of this homogeneous equation, right? Then you see that any constant alpha u1 plus beta u2, where alpha and beta are constants, not dependent on x. So x is only appearing here. u1 and u2 are of course functions of x. But alpha and beta are constants, then this is also a solution, right? That just follows from the fact that these are linear equations and the right hand side is 0, right? So it immediately follows. So therefore it's a vector space. The space of solutions is a vector space. Now what we will show is that actually this solution has only two linearly independent, I mean this vector space is two-dimensional basically. So we will show now that so this is a vector space. So this forms a vector space, and we'll show now that it's two-dimensional. Okay. So let's see how we proceed. So I can just remove this. So we'll be just first discussing only the homogeneous. Okay. So in fact, what we will finally show is that if one of the solution is known, somehow suppose somebody has given to you one solution, then you can find the second linearly independent solution. Okay. So of course, to find the first solution itself is quite difficult. But we will, later on we'll discuss series solutions and so on. You can develop power series solutions to find say the first solution, and then the second solution you can obtain by the methods we'll describe now, I mean today. Okay. So I mean let's suppose we start from two solutions u1 and u2, and suppose they are linearly independent. Suppose these are linearly independent. Okay. In fact, I mean, so what I will first show is that the dimension can be at most 2, which means that any other solution I should be able to write it as linear combination of these two. Okay. So a maximum dimension is 2. Okay. So of course, so that means that what does it mean? It means that alpha u1, remember this is functions of x, alpha u1x plus beta u2x. If you consider this equation, this is equal to 0, then the only solution is alpha equal to beta equal to 0. That's the definition of linear independence, right? Then, I mean, this statement would imply that the only solution to this equation is alpha equal to beta equal to 0, right? That's the linear independence statement. Okay. So given this equation, let's take a derivative also of this equation. So you'll get alpha du1 by dx is a function of x plus beta du2x by dx. That's also equal to 0. I'm just taking the derivative of this equation, right? So in all of these discussions, I'm going to assume that this u1 and u2 are differentiable, right? I mean, in fact, for this equation to make sense, at least it should be twice differentiable, right? So, okay, so so this is exists. I mean, so by assumption, these derivatives exist. Okay. So now you see that if look at these two equations for two unknowns, alpha and beta, right? And if I mean, and we know that the only possible solution to this equation is alpha equal to beta equal to 0, right? That means, I mean, this would be that means that this determinant of the coefficients of alpha and beta from these two equations. So we are thinking of alpha and beta are unknown, and these are given, right? So then the determinant of these coefficients, which is u1x, u2x, du1x by dx, and du2x by dx, this determinant, if this determinant is not equal to 0, then this is guaranteed, right? Because then you can invert this matrix, this coefficient matrix, and then you see, then you get this matrix acting on alpha beta equal to 0, 0, and then if this matrix, if this determinant is not equal to 0, then it's invertible, and then the only possible solution is alpha equal to beta equal to 0, right? So this, by the way, there's a name for this. This is called the Wronskian. Wronskian, I mean, is Wronskian. So Wronskian is the notation is Wronskian, and you put here u1 and u2. So given any two functions u1 and u2, you construct this Wronskian. Okay. I should say that this Wronskian has a very nice property, actually. So if you take this Wronskian, and let's take the derivative. I mean, this Wronskian, of course, depends on x, because both u1 and u2 depend on x, right? So Wronskian depends on x through u1 and u2, because they depend on x. So we take a derivative with respect to x of the Wronskian. Well, that by definition is simply the derivative. So what we will get, by the way, you know how you take a derivative of a determinant is a sum of two terms, actually, right? Because okay, so let's explicitly write down what it is. So w is simply u1 du2 by dx, this determinant, minus u2 du1 by dx. Okay, so so if I take dw by dx, that's the same as, okay, you take derivative. There are two terms when the derivative hits here or the derivative hits there. So when it hits here, you get du1 by dx, du2 by dx, because derivative obeys Leibniz rule, no? Plus u1 times d2 u2 by dx2, and then similarly minus the derivative hitting here gives you du2 by dx, du1 by dx, and then when derivative hits here, you get again the same minus sign, u2 d2 u1 by dx2, right? But now notice that this cancels. Okay. So I mean, in fact, you can see the rule of the differentiation is that if you combine these two terms, that is simply the determinant obtained by just applying the derivatives here on the first row, right? if you apply first derivative on the first row, you will get precisely du1 by dx times du2 by dx, this one, minus du2 by dx times du1 by dx. And if you look at the last two terms, I mean this term, second and fourth term, that's the same as applying derivative in this second row, right? So the rule for computing, I mean the derivative of determinant is you just take derivatives of each row or each column, it doesn't matter, each row, and add them up. So anyway, here I did explicitly because it's a 2 by 2 determinant, so you can explicitly work it out. Otherwise, if it's 3 by 3 determinant, in order to write down this whole thing, it will take a long, I mean, time and space, you know. But here you can do it. So you see this object. So this cancelled. This cancels with that because this is the same term, right? But this, of course, does not disappear. So you get this expression. But on the other hand, if I use this equation, then the second derivative, which appears here, I can write it in terms of first derivative and the function itself, right? So let's see what it is. So the first term here is u1 divided by a, so 1 over a times minus b du2 by dx minus c u2. Right? I just use the fact that u1 and u2 are solutions of this equation, right? So therefore, if I plug it here, plug u2 here, then that is 0 by definition because it's a solution. And then I just substitute this du2 by dx2 from this equation. So again, I'm assuming that a is not 0. So the region of x I'm looking at, a is not 0 there. Otherwise, you cannot divide it. And similarly here, you get minus u2. And now again, I use the fact that u1 is a solution of that equation. So again, 1 over a times minus b du1 by dx minus c u1. Right? And now you see that again, this term cancels with that, right? Because this is u1 u2 times minus c over a. And that is u2 u1 times minus c over a, so that cancels. So what is left over is that, so what is left over, if you look at this, so this is minus b over a is a common factor in both the terms. And after that, what you're left with is u1 du2 by dx minus u2 du1 by dx. But that was the Wronskian itself, so times minus b over a, right? So what we are saying is that this is equal to minus b over a times w. So we are seeing that w satisfies a first order differential equation, right? So dw by dx is minus b over aw. Okay. So in fact, we will use this fact to, you remember I told you that if I know one solution, then I can construct the second solution. Okay. And that will be by solving this first order differential equation. And then we will see that in a short while. Huh? But okay, first let me go back to the original statement. So what we want to show is that if u1 and u2 are linearly independent, then any other solution I should be able to write as a linear combination of u1 and u2, right? That means that the maximum number of linearly independent solutions is simply 2. Okay, so this was, let me just keep it here, dw, this equation, dw by dx is equal to minus b over a w. So this is the first order differential equation. Okay, so I can erase all this part here. Okay. So now let's consider, suppose there is another solution also, right? So here u1 and u2 are some given to you, right? They are linearly independent. Now let's assume there is also another solution u. Huh? So suppose there is another solution. Solution u of this equation, right? Then what we have three actually equations, right? So let's see, let me write it like this. So A d2u by dx2, I mean this u, this u, another solution, right? That satisfies that equation. So it is true, b du by dx plus c u equal to 0. And then, of course, then I also know that u1 and u2 are also solution of this equation. So I have also a d2 u1 by dx2 plus b du1 by dx plus c u1 equal to 0. And similarly, a d2 u2 by dx2 plus b du2 by dx plus c u2 equal to 0, where u1, u2 and u are given to you, right? I mean, so I said u1 and u2 are two linearly independent solutions, and the u is another solution, right? So these are given to you now, and they all satisfy the same equation. Now think of this equation as an equation for a, b, and c, right? Linear equations for a, b, and c. Okay. So suppose a, b, c are unknown here. And u1 and u2 are given to you, which means, of course, not only u is given, but also the derivatives are given, because if you know the u as a function of x, then you can take derivative. So all these are known to you, right? You think of this now, this as a equation for a, b, and c, right? Then for this equation to have non-trivial solutions for a, b, and c, the determinant of the 3 by 3 matrix must be equal to 0. Otherwise, the only solution will be trivial solution, a, b, and c equal to 0. But then the equation is trivial equation. If all these coefficients are 0, there is no differential equation here. Is there, right? It's right. So we want a, b, and c to be non-trivial. So we want to have a solution for a, b, and c which is non-trivial, not all 0. No. But that means that this 3 by 3 determinant of this 3 by 3 matrix. I mean, in other words, I'm saying that you just write this 3 equations in the matrix language. So if you write it in the matrix language, it's simply d2u by dx2, du by dx, u d2 u1 by dx2, du1 by dx, u1, and d2 u2 by dx2, du2 by dx, u2, this 3 by 3 matrix multiplying a, b, and c, that's equal to 0, 0, 0, right? These 3 equations I can write in the matrix language like that. Okay. Now for this equation, this is homogeneous linear equations. So for these equations to have any non-trivial solutions for a, b, c, this determinant must be equal to 0, right? But if this determinant is equal to 0, the columns are not linearly independent, right? So that means, for example, the u1 and u2 are not linearly independent. And similarly, of course, these are also not linearly independent. Similarly, these are not linearly independent, right? So in particular, u1 and u2 are not linearly independent. Therefore, we see that u is a linear combination of u1 and u2, right? So the necessary condition for, so let me just write this down again. So necessary condition for non-trivial a, b, and c to exist, to exist as solutions of this equation, that is the determinant of this let's call this matrix as M. Let's call this matrix as M, right? Then determinant of M must be equal to 0. And this implies that u1 and u2 are linearly dependent. By assumption, u1 and u2 are not linearly they are linearly independent. So what this means is that I should be able to express u as a linear combination of u1 and u2. Right? So this implies that u is equal to some number c times u1 plus another number d times u2. where C and D are some numbers. Okay. Because this has to be true for every x, you see. For every x, this has to be true. They are linearly dependent. So as a function, it should be linearly dependent. So what we are saying is that u of x is equal to u1 of x to x. Okay. So that proves that the maximum dimension, I mean the dimension of this cannot be greater than 2. Dimension of the space of solutions cannot be greater than 2. So now the next point is to show that if somebody gives me a u1, one of them, right? By the way, there's again another terminology. Any two linearly independent solutions of the second order differential equation is called a fundamental set of solutions, right? Just a terminology, fundamental set. When you say a fundamental set of solutions, which means that you have a set of linearly independent, I mean a basis, basically basis of the solutions of the space of solutions. So that's called a fundamental set of solutions. Of course, there's nothing unique about it. No, it's not. As in a vector space, you can choose any basis, right? Many different bases you can choose. So there's nothing unique about it. But okay, it's a fundamental. That's why we say a fundamental set, not the fundamental set. Okay. So now we say that suppose that u1 is given. We want to construct, suppose u1 x is given, which means this solves that equation. This is one solution, right? Then we want to find the another solution u2, which is linearly independent of u1, right? So we want to construct u2, which is again a solution of that equation, and which is linearly independent. Independent of u1. Okay. And this is done by a method which is used again and again. This method is called the method of variation of constants. Okay. So this is a method called a method of variation of constants. I don't know why this terminology came historically, but okay, this is what it's called. Okay. So the idea is the following. Let us try to make an ansatz. This is called, to write an ansatz for u2. Let's call u2 equal to, let me use the same symbol, h. So u1 of x times h of x. Okay. So this is an ansatz. Okay. So we'll plug that in here. Okay. Use the fact that u1 is already solving, is a solution of that equation. Then we will be able to get an equation for h. Okay. And it will turn out the equation for h will be first order. I mean, you can make it into a first order differential equation. Okay. It will not be immediate. You have to do several steps in order to get there. But what we will finally be able to do is we will be able to solve for h explicitly. Okay. Because first order differential equation you can solve by as in terms of some integrals. No? We can and then we will show that this h is in fact. And then we'll show that these two are linearly independent. Okay, so once you know h, then you can just get back u2, right? So this is a strategy. Okay. So let's plug that inside this equation. So let's see. So what this means. So d u2 by dx is simply d u1 by dx times h plus u1 times d h by dx, right? Again, I just use the Leibniz rule. I mean, some places I may not write x, but I hope it's understood that these are all functions of h, x, functions of x. Now let me take second derivative, d2 u2 by dx2. I need that because I need to plug this here. No? So I need the first derivative and the second derivative. Well, let's again do the same thing. So there will be one term which will be d2 u1 by dx2 times h. Another term will be du1 by dx times dh by dx. Okay. That's coming from derivative heating here. Then there is a derivative heating here. So again, you will get a term du1 by dx times dh by dx, but that's the same term, right? So it will give you a factor of 2 when you add the 2. And then a derivative heating here, which will be u1 d2h by dx2. Okay. So that's that. And now let's plug this in here. So let's multiply this a with this. So you get here a times d2 u1 by dx2 h plus 2 du1 by dx dh by dx plus u1 d2h by dx2. So that's the first term. The second term is plus b du1 by dx times h plus u1 times dh by dx plus c times u1 times h. Huh? I just plug this u2. I just plug the u2 here, so I get this expression, and that's equal to 0. So this is the equation. Okay. Good. Now let's focus on this term, and that term. So in all these three terms, h is a common factor, right? So I take the h, the common factor, out, and then what is left over? You get here a times d2 u1 by dx2 plus b times du1 by dx plus c times u1. But that was the original equation, and we already assumed that u1 is a solution, right? So these three terms cancel each other, so they vanish. And then what is left over is just the remaining terms, and so let me write it like this. So a times u1 d2h by dx2, that's this term. And then there are two terms which involves dh by dx. So let me combine them, dh by dx. And then here you get 2a du1 by dx plus bu1. Right? That's equal to 0. So now you see, even though it's a second order differential equation for h, but it's actually a first order differential equation for dh by dx. Right? So you can solve for dh by dx. And then once you know dh by dx, then you can again integrate it once more to get h. So this equation, I can write it in the following way. Let me call, I don't know, let's call dh by dx is equal to something. Give some name to it. Let's say f. Okay, I just give a name to it. Then this equation is a first order differential equation for f. And you get df by dx divided by f. So I divide by this f and take this on the other side. So you get here this is equal to minus, and divide everything by a u1. So you see a cancels. So you get here 2 du1 by dx divided by u1 from the first term. And from the second term, you simply get minus b over a, because u1 cancels. Right? So the solution of this is easy. So this gives you that f log f, right? This is simply derivative of log f, right? And this is a derivative of 1 over log of 1 over u1 square, or in other words, this is the same as minus 2 log u1, right? Which is the same as log of 1 over u1 square. And then I have the integral of so let's say minus some fixed point x naught to up to x of b over a, b y a y dy. That's up to a constant. Up to, you can of course add a constant, up to some constant. That's the solution for, you can explicitly see. If you take derivative of this side, you get df by dx divided by f. That's the left hand side. You take the derivative of that, you get minus 2 du1 by dx divided by u1. You take derivative of that, x only appears in the limit point, I mean one of the endpoints. So that simply gives you the integrand evaluated at x, which is that. I mean this is all x, right? Here is all x. Okay. And then the constant you can of course add. I mean the derivative of this constant is 0. So this is the solution of that equation. Yeah. I mean, so what is, so let me call dh by dx is equal to f. So what is df by dx? Df by dx is simply take a derivative of that. One more derivative of that, right, which is d2h by dx2. Right? So I write this as df by dx. And then this whole equation I have divided by a. So I have, in order to obtain this equation, I have taken this equation and divided this entire thing by a times u1 times dh by dx. So which means f. So a times u1 times f I have divided. So when you divide that, first of all a u1 cancels, and then you just get a 1 over f because you are also dividing by f. No? So that's this term. And similarly here I just did that. All right. So now let's see. Let me erase this part. So what we are seeing is that f therefore is equal to 1 over u1 square, right? I just take the exponential of both sides. So this just gives you f, that gives you, there's a e to the power of minus 2 log u1, which is same as 1 over u1 square, times e to the power of minus x naught to x by over ay dy. Okay, and this constant again, I mean, let me put here it's like log of a constant. Okay, log of c. Okay, doesn't matter. If a constant I can write as a log of some another constant, so that will just come as a constant here. So f is simply that. Okay, now now I know f, so I can compute h. Right. So h is simply another derivative of that. So h. So this is f of x. Let me write it like this. So u1 x square. This is a constant. So h of x will be integral of f of y dy from some fixed point to x, right? Because yeah, dh by dx is f. So f. So we can just plug this in here. So this is simply x naught to x, some constant 1 over u1 x square, u1 y square, because this is f evaluated at y. And then here you get e to the power of minus x naught to y. And now I should choose some other dummy variable here, b of, I don't know, what shall I call, y prime over a y prime dy prime. Okay. That's plus a constant, again, because this is a first order, I mean, what we have is this is dh by dx, right? So I'm solving for now h. So of course to this I can add any constant, another constant. This is one constant, this is another constant. Plus, I mean, so you can add something else, c, say small f. This is the constant, so plus f. So this is the most general solution for h. As expected, there are two constants, right? Because this is after all, for h is a second order differential equation, right? So you should have two constants. There are f. I mean, there's one constant already in solving this first order differential equation, and that is that c. And then another constant is this f, which when we solve again this another first order differential equation. So total number of constants must be 2, which is what we are finding. Okay. Now this constant is completely irrelevant. This constant is completely irrelevant. Why? Because after all, I mean, I mean, we are not interested in finding h. We are interested in finding u2, right? u2 was u1 times h, right? So if you multiply this with the u1, you see this is just some constant times u1. But we are not interested in that, because after all we are interested in finding a linearly independent solution. And we anyway know that given a solution I can always add another solution to that. It doesn't change, right? and u1 we already know. So this is a irrelevant constant. And similarly, this constant is also irrelevant because, I mean, in other words, first of all, let me see. This f doesn't give me any new information. Okay, so I might as well put f equal to 0. Right. So this I can set to 0 already, because this simply, when you multiply with the u1, just gives me back the first solution that we already had. So that's irrelevant. And similarly, this is also not relevant because, I mean, so you take h times u1, so this whole thing times u1. Well, I'm always given a solution, I can always multiply by a number, doesn't change anything, right? So this c also you can choose anything if you wish, and you can just make it 1, it doesn't matter. But the important point is this part, the functional dependence, how it depends on x. Okay. Yeah. No, here it's completely, I'm not assuming any bound. There's no boundary condition here at this stage. That will come discuss later. At the moment, what we are saying is that locally, this is all basically we are doing a local discussion. In some local region, I'm trying to find 2 independent solutions. Now, of course, so what will happen is that a general solution will be a combination of these 2, right? With say 2 constants, C1 and C2. So it's C1 U1 plus C2 U2. You determine C1 and C2 by imposing the boundary conditions, right? But at the moment, it's free of boundary conditions, this discussion. Okay, so now let's multiply. So let's try to now see what is this Wronskian, right? So U2, therefore, U2 is simply as we said, U2 is simply this H given here times U1. Right? So now let us plug this inside this Wronskian. Right? So Wronskian of U1 U2 is U1, determinant of U1, U2 which is U1 times H, okay, and du1 by dx. And here we'll get 2, when you substitute U2 there, you'll get 2 terms. One is du1 by dx times H, plus other is U1 times dH by dx. Right? So I have to compute determinant of that. Okay. So let's see. So that means this times this thing minus this times that. Right? But notice that this cancels with that term, because this is U1 du1 by dx times H. This is also U1 du1 by dx times H. So this cancels. So only thing that survives is this times that. Okay, which is U1 square times dH by dx. But dH by dx is that, right? So this is, in fact, you see the U1, this is all at x, this is all at x. So you get, sorry, U1 square, this U1 square is there. Okay. U1 square, so when you substitute that, this U1 square cancels, okay, and you are left with, okay, some constant, that's not important, e to the power of minus x naught to x by over ay dy. This is what is a Wronskian. This is the Wronskian. See, Wronskian is simply this exponential, this part, up to some constant. So, but this exponential of anything cannot be 0, right? So therefore, you conclude that this Wronskian is not 0, right? I mean, I'm assuming, as I said, a is never. I mean, this could become 0 if this was plus infinity. E to the power of minus infinity is 0. But we are staying away from any region where y is 0. I mean, ay is 0, right? So in that region, this will be some finite quantity, right? So it will never, exponential of that will never be 0. Yeah, exponential of that will never be 0. So Wronskian of U1 and U2 is not 0, but that implies that U1 and U2 are linearly independent solutions, right? So this way, we have a proof that at least in some local region where, I mean, you don't have any singularity, right? There you have two linearly independent solutions, and just precisely 2, not more than that. Now, of course, here I've assumed that U1 is given to you. I mean that you have found at least one solution, right? But that we will discuss later when we will show that there is always, you can write down a power series solution near non-singular points. Non-singular points are precisely those points where A is not 0. So near, so some, if at some x A is not 0, then you just look at some small region around it. There you can always write down a power series solution. We will discuss that later. So for the moment, I'm assuming that U1 exists, and then U2 you can find. Okay. Okay. So this was for the homogeneous. Now what about the inhomogeneous inhomogeneous equations? Because many times in physics you come across inhomogeneous equations also, right? Like for example in Maxwell's equations, you will have some left hand side, some differentials acting on something, say potentials, gauge electromagnetic potential and so on. And right hand side will be charge density. So it may not be 0, right hand side may not be 0. So in general you do encounter inhomogeneous differential equations. So let's go back now to some Q of x. Okay, so in this case, what can we, I just erased unnecessarily that, okay, anyway. Okay. Once again, I will assume that U1 is given to you. U1 is what? U1 is the, before even discussing that. I mean, so let's look at this solution. Suppose I have somehow managed to find one particular solution of this equation. Okay. Then to this I can add any combination C1 U1 plus C2 U2, where U1 and U2 are two linearly independent solutions of the homogeneous equation. Okay. So these are the homogeneous solutions of homogeneous equation, which means right hand side is 0 for these guys. But that's obvious, right? Because we are saying this satisfies inhomogeneous equation. Then to that I can of course add this, because these are annihilated by this differential operator, right? So that's obviously a solution. So again, solution is parameterized by two parameters, but it's not a vector space really. This is kind of a shifted vector space. I mean, you have shifted the vector space so that 0 is not part of the vector space. Because UP is a particular solution. So it's not really a vector space. But okay, in some sense, it's still a two-parameter family of solutions. Okay, so now the question is, how will I find UP? Right? The technique is again the same, and I mean again the same. What is this method of variation of constants? So let's again put UP as some U1. I mean, say take one of them, U1 times some function V. So this is a function of. And once again, plug that inside here. Okay. So what I will find here is, yeah, so I think that's why I necessarily erased that part. So we'll get here A times, so okay, let me write again. D2 U1 by dx2 V plus 2 du1 by dx times dv by dx plus u1 d2v by dx2 plus b times du1 by dx plus times v plus u1 dv by dx plus c times u1v, that's equal to q, right? I just substituted this in the second derivative, right? I mean, these numbers, by the way, you can easily see how these are combinatoric numbers actually, right? Because you have, see here, you have two derivatives acting here. So what are the possibilities? Say both derivatives act here, or both derivatives act there. So those are those two terms. But then there will be a term where one derivative acts here and other derivative acts there. But so let's say the derivative which acts here I have to pick one out of the two derivatives. How many ways I can pick? There are two ways of picking it up, right? So that's why that factor of 2. But once that I have picked one derivative acting here, then the second derivative has to act there to get such a term. So then there are no further combinatoric factors here, just a factor of 2. So okay, so you get this equation. But once again, you see this term, if you take again this term, and that term, that is 0, right? Because U1 solves the homogeneous equation. So that's 0. So you are left with equation which is A U1 d2v by dx2 plus plus the term which is dv by dx, and then you get here so yeah, 2a du1 by dx plus bu1, and that's it, right? Equal to q. That's the equation. So it's again, you see, a first order differential equation for dv by dx. So this procedure is the same. You try to solve it in 2 steps. So 2a du1 by dx. How is this? Yeah. So so once again, we divide this by au1. Let me just divide this by au1, this entire equation. So you get here this here, this becomes this divided by u1, and that becomes b over a, and here this becomes q divided by a u1. That's the why is it? It seems something is missing in this equation. On the right hand side there should be now, I'm looking at equation 2.19. On the right hand side I don't see a. No, okay, they have defined, okay, so sorry. They have defined q over a, they have defined, they call it f. That's all, okay. Yeah. Okay, now this was, we already said. What did we say? The Wronskian was this quantity. So now you can see that, in fact, this is what we did for this object. This quantity 2 over u1 du1 by dx plus b over a is simply, this is how we obtain that. Let me just write this down. This is equal to, let's call it 1 over r. In fact, I'll just let me use the same thing, dr by dx. Okay. And in fact, we are calling f, right? This is what it is, f. F is that. So this was df by dx 1 over f. Right? This is how we obtain this solution. I mean, in the previous, when we discussed this, when we obtained the second homogeneous solution, U2, this is what we did, right? We wrote this. I mean, this was the solution of that equation, right? Because you get log of f here, you get sorry, there is something again wrong here. No, probably it is not. It's not. Okay, maybe it's not exactly f. Let me use take the separate symbol r. I'm not sure whether r is the same as f. Okay, so let's do that. So this of course, what is the solution of this equation? Solution of this equation is simply r is equal to u1 square. Okay, yeah, u1 square. Times e to the power of minus e to the power of b over a. No, okay. I think it's just the inverse of that. I think this r is simply 1 over f. E to the power of integral of b over a y dy. Okay, x naught to x. This is r. Yeah, this is r. It's just the inverse of f actually, right? Because you see 1 over f will be u1 square up and this sign will be plus. Correct? So this is the inverse of f. So okay, so in fact r is simply 1 over f. That's what we are saying. Because in fact for the f the equation was this, right? Df by dx 1 over f was simply minus of this quantity. It's minus 2 over u1 du1 by dx minus b over a. This was the thing. So there's a negative, you see. Right? So I mean this is d log r by dx. This is but that quantity is the same as minus d log f of x. So r is equal to 1 over f. Okay. So let's substitute that here in this equation. So you get here d2v by dx2 plus 1 over r. So I'm just calling this is 1 over r dr by dx. Right? So 1 over r dr by dx times dv by dx. That's equal to q divided by a u1. Okay. Where r is that. Okay. So now let's multiply both sides by r. So you get here r. Okay. And now this left hand side is a total derivative. These two things together is d by dx of r times dv by dx. Right? Because when this derivative hits here, you get that term. When this derivative hits here, you get that term. Right? That's equal to q r over a u1. Okay. So now we can integrate. Right? So I mean just two steps of integration. So this tells you that r dv by dx is equal to the integral of from x naught to x of q y r y over a y u1 y dy. Okay. This is the left hand side is at r at x. Okay. That is just the solution of this equation. And then you can do one more integral to get the v. Okay. This is, I mean, it was obvious that once you have obtained a first order differential equation for dv by dx, you can solve that by the methods that we discussed before for the first order differential equation. I'm just writing down explicitly these answers. So this gives you v is equal to 1 over r. So y dy, so v of x naught to x. And then all the right hand side evaluated at y. So you get here x naught to y. And then you have to use a dummy r y prime over y prime dy prime. Okay. So this is the final. So there's a double integral, right? There's one integral here from x naught up to y, and then there's a y integral from x naught to x. The y prime integrals from x naught to y, where r itself is given in this way. So it's a rather complicated expression, but nevertheless you can do it. You can express it. Once you are given a, b, and u1, etc., you can, in principle, work out this integral or put it in the computer to work it out. So, yeah. So that's. So it's not. I mean, it's not too. I don't know. It's not very illuminating. But I mean, these final expressions are not very illuminating, but the method is very clear, right? The main strategy here is when you write it in terms of this product, I mean, anything you express in terms of something times the solution of homogeneous equation, then the result is that you get a differential equation, first order differential equation for dv by dx. And then you can solve dv by dx, and then once you know that, you solve for v, right? So this is the main method here. Problems in physics are more complicated because first of all, they're not I mean, it's a partial differential equations there, not in one variable, right? It's much more complicated. Yeah, this is just to show. I mean, this in one dimension. I mean, in fact, in this entire core chapter, I'll be only discussing one-dimensional problems. Maybe towards the end, I say something about spherical harmonics, but not more than that. I mean, already the differential equation in one variable is pretty complicated. When you try to find, I mean, this was assuming u1, you know u1, but already u1 is difficult to find. I mean, okay, if you find it, then the other things you can find. So I will, yeah. Sorry.
What is the most generic form of for-solving differential?
It's okay. I mean, I will describe something called the Green's functions, the method of Green's function. But again, I will do it only in the one dimension problem. But that is a method which is more useful in higher dimensions. Yeah. In 3 dimensions, typically, you solve the problems by using Green's functions, actually. Right. So, for example, Maxwell's equations, if you're given a charge density somewhere, you use Green's function to evaluate the solution, the equation. So I will describe the Green function method, but I will show it only in the one-dimensional problem. Yeah.
So this is in general, that if the form of Q is
complicated.
No, not complicated. This is we work in general, okay?
Yes.
But if the second number is if we know the form of the second number.
Yes.
If you can we use this method of we use directly the form of second number?
Yeah. I mean, so in this equation, I'm assuming that A, B, C, and Q are given to you, right? So Q is given, whatever it is. I mean, maybe it's x, maybe x squared, maybe e to the power of x. Who knows? Whatever, something is, but it's given to you, right? Only unknown thing is u here, right? So one. And I'm also assuming that u1 is somehow we have found a u1, a one solution of the homogeneous equation. Okay. Then given that we have all these expressions, you see the point is that b and a are given to you, so you just plug that in here and do the integral, right? Of course, I mean, for very, very complicated functions b and a, it will be difficult to find analytic expressions for those integrals, no? But maybe you can do numerically, try to compute it, put it in the computer or something, try to compute. But okay, suppose that b and a, etc., were sufficiently simple functions, you could actually integrate it, right? And you would get this. These are indefinite integrals, by the way, not definite integrals, because x is free here. This x naught, you can fix anything. You can choose it to be 0 or whatever. You can fix some number here. But this x is free, right? So it's a indefinite integral. Okay? So you cannot use all these contour deformation techniques and so on to evaluate that. Those you can do only for definite integrals, right? And even then, sometimes, not always. But so here, okay, so this is, so if the functions are sufficiently simple, perhaps you can actually get an analytic expression for it as a function of x, right? But that's not enough here. Here you need several integrals. Even if that can be done, it's not clear whether you can carry out this integral. That depends again on how simple q, r, etc. are. No? If they are sufficiently simple, you can explicitly do it. Otherwise, you have to put it in the computer, or make some numerical in some small region of x. Maybe you can try to make some approximations and get it. And then on top of it, you have to do again a third integral. So there are lots of integrals here. Right? So yeah, there's no guarantee you can get analytic expressions for these things. Yeah.
What about if, what will happen if C of x is equal to 0?
If
C of x.
If C of x is 0, then this already becomes a first order differential equation for du by dx, right? If C is 0, then this is already a first order differential equation for du by dx. So then you can directly, I mean, then you can directly work out, right? I mean, you don't even need to know a u1 then, right? Because in that case, you can completely solve the problem already for the homogeneous equation itself. So you can find out both u1 and u2, right? If C was 0. Right? I mean, is that clear? I mean, if suppose C was 0, then your equation, first let's look at the homogeneous equation. It's simply A d2u by dx2 plus B du by dx. That's the homogeneous equation, right? And this you can solve because this is the first order differential equation for du by dx. So first you solve for du by dx as a one integral, and then you solve for u as a second integral, right? So you can find both the solutions. And then also you can find the inhomogeneous solution by going through this procedure. Yeah.
If you are free to choose x and x naught, can we have standard integration?
Yeah.
And for each integration, we choose a different.
Sure, you can choose different x. Yeah.
Yeah.
I mean, yeah. By the way, I kept using x naught in all these base points, no? But it's not. You can just choose different, but fixed points, right? I mean, not. It should not depend on this y. Something independent, but this x naught, these two different x naught need not be the same, could be different. Okay.
So is it the solution unique? I mean, if I can choose in my vector space different domains,
Yes.
then is the solution unique? I mean,
So you are saying that so in some domain I choose one x naught.
for instance, for the first integration,
Yes.
I choose somewhere my domain, so the integral is
Oh,
pt, and then for the next I choose another.
No. I mean, you'll have. I mean, you can get a solution there and only in the overlap of all these domains.
Okay.
If the overlap is null, then no. Then
Okay. But maybe still the solution. Maybe it works for the differential equation.
I mean, as a formal expression, this is fine as a formal expression. But you are saying, okay, if I can integrate this expression only in some region, right? Whereas this integral I can only integrate in another region, then you cannot. Yeah. Was there anything else? Yeah. You might say, you know, what happens if I change these x naughts? I mean, these different points here. No, I have lots of arbitrariness here. I have an arbitrariness in choosing this, right? Arbitrariness in choosing these constants. There are lots of constants which I have set them to conveniently to 1, right? In all this. So in various places, every time you integrate, you have various constants. You can put them. But in fact, you can try to show that. I mean, try to put all the possible constants which are there. There are also this arbitrariness in this choices of the fixed points, right? But all that amounts to is, you see, after all, this up was v times u1. Right? So take this v and multiply by u1. That is a particular solution, right? But a general solution of this equation was up plus any constant times u1 plus any constant times u2. That was the most general solution of that, right? So you should be able to show that the choosing this different constant, different values of constants, different initial points of integrations, all that actually amounts to just changing the c1 and c2. That's a good exercise to check, actually. In fact, I mean, I hope I have not made any mistake in the final formulae. But I mean, in fact, that's one way to check whether you have made any mistake because it's very easy to make some algebraic mistake, signs, this or that, no? But if you see that this arbitrariness in these choices just amounts to arbitrariness in choosing c1 and c2, then that is a good check that you have not made any algebraic error in between. Right. So, yeah. I mean, for example, I mean, if let's take so, I mean, if I change the x naught, what does it do? I mean, this, if I change x naught, this is simply, I can to say x naught prime, right? So x naught prime to x, okay, this integral. But then this is the same as x naught to x plus x naught prime to x naught, right? Okay, this was the original one. But what is the result of that? The result of that is some constant, because that's independent of x. So that will be just, there was also another constant here which I have left out. But that just is absorbed in that constant in front, right? So typically changing these things are not going to make any much difference apart from a multiplicative constant or additive constant. In this case, additive constant, because it's not exponential. Here it's exponential, so it's a multiplicative constant, right? So for example, here if I had changed say this value, x naught value, so then it's going to be just a constant multiplying, I mean additive constant multiplying dy by ry, right? But when then you plug all these things back, and you can try to show that all that really is just choosing different values of C1 and C2. You can absorb it in the choice of C1 and C2. Try that. Yeah. For example, this multiplicative constant is irrelevant, you see, because in the final formula, if you multiply r appears in numerator and denominator. If you multiply by that constant, is irrelevant, right? But these things, these constants, when you change, that is additive, and I think you should be able to show that those additive constants just boil down to choosing C1 and C2. Okay. I mean, there you have to again use the fact that u2 again was expressible in terms of u1 times that little h, right? That little h was again given in terms of those integrals of f, etc., where f is 1 over r, right? So you have to use that to I mean, yeah, is that I think, yeah, okay. Okay. So now let's, what is the next topic? Sometime. Right. So let me describe now, before describing the power series solution, okay, the power series solution to find. Okay, let me see. These expressions are valid whenever, in everywhere where a does not vanish. You see, because I mean the only thing is that if a vanishes, then there is a problem here, right? This integral doesn't make sense. I mean, this integral will blow up there, right? So I'm assuming that whatever this from x naught up to x, that region, the a doesn't vanish. This integral will make sense. Yes.
If you want to use the same domain, the domain in which our f(x) is not defined, you can't use our x. You have to choose a domain in which our f(x) is defined before using.
I mean, generically speaking, this will not be, there will be not a divergence. I mean, the divergence will be generally some at points, no? I mean, for reasonable functions. It won't be that function is just zero in continuous places. So maybe there is some region where this a is 0. Let's suppose a is 0. There I cannot talk about these integrals. I mean, they don't make sense. Huh?
Yeah,
fine.
My question is about the choice of x naught and x naught prime, for example.
I mean, so I'm going to take a region where, I mean, you have, say in some place a is never 0. Right? So, and I will be talking about x is somewhere here, and x naught is some fixed point. Some fixed point inside the same place. No? So, I mean, it's not just enough. It's not enough that, I mean, you have also other things that are multiplying here, right? I mean, you have to make sure that u1 doesn't vanish. So that this integral, for example, is not just the a doesn't vanish, but also u1 should not vanish. You know, so I'm looking, take some region where neither a is 0 nor u1 is 0, right? So you have, depends on the problem which what you are looking at. So okay. I mean, if these are not 0, then R is also not 0. So in the region where U1 is not 0, A is not 0, well, A is not 0, this integral is defined, U1 is not 0, so this expression R is not 0. So you can come back here and integrate those expressions. So in some region where A and U1 is not 0, there you can do this integral. But I mean, see, you can push it all the way to even the places where, say, A1 goes, A goes to 0, say somewhere out here. You can go as close as you wish, right? And that is just going to tell you that your solution has some divergence there. You can push it as much as you can. Right? As a formal thing, if you give me a function A, I mean, all this is saying is that this is an indefinite integral. I mean, the reason for the choice of x0 is because I want to give a definite, I mean, the two limits, right? But if you, I mean, if there's a differential equation, d of something, I don't know, d of zx dx is equal to something here, say f of x, right? If this is given to you, and if you can already directly guess the, I mean, you know, this may be some function, I don't know, for example, let's say x divided by x minus 1, for example, right? Now this is divergent at x equal to 1, right? However, you know that you can directly integrate this, right? I mean, this will just be, you can write as minus 1 plus 1, which is 1 plus 1 over x minus 1. So therefore z is simply x from that term, right, plus log x minus 1. So I mean, but I'm just writing it as an integral, right? It is an integral, but here I don't care about x0 at all, you see. So it's but of course, in general, what will appear here will be some, could be very complicated functions. You will not be able to just, you know, easily integrate it, right? I mean, there is a divergence here, but of course, indeed, the solution also has a divergence as x equal to 1. Right?
In the case of U1 is equal to 0, since we have two solutions, homogeneous linear solution,
Yes.
can we use the same method with the other solution?
Yeah, you can choose U2. Yeah, sure, you can choose U2, right? Yeah. Right, yeah. Okay, now let me go to the, at least start the discussion about the Green's functions. Okay, the powered solution will come later. Let me see, where is it? No problem. Yeah, series solutions in differential equations. Yeah, that will come later in the section 14th. So we will postpone the discussion of how you find the U1 for some time. Because Green's function will take at least 2 or 3 lectures.
If we do much on Green's function, it's better.
Sorry?
If we do much on Green's function.
Yeah, but as I said, I will be doing only the one-dimensional problem. Okay, and even to write down the Green's function, you need to know. I mean, at least in general. I mean, if you want to write down the Green's function, you need to know a set of fundamental functions, right? Fundamental solutions. It will become clear, I mean, when I go through some examples for the Green's function, that if you know the fundamental solution, you can immediately construct the Green's function, right? But the Green's function is quite useful in, because Green's function, I mean, typically the fundamental solution is not the only, I mean, as you're saying, for a physics problem, there will be boundary conditions, right? So you have to solve the equation with a suitable boundary condition. Then there are inhomogeneous terms and so on in general, right? So in those cases, once you know the Green's function, which is constructed entirely from the fundamental set of homogeneous solution, then using the Green's function, you can express the general solution, right? But even there, you see, you need to know the fundamental solution. That's the problem. In 3 dimension also, you see, in higher dimension in general, it's very difficult to consider the Green's function, okay? However, typically the examples that you have, I mean, typically the differential equations you get are Laplacians, right? The differential operators are like second order differential operators are Laplacians. For Laplacians, you can easily construct the Green's functions. Right? But that's a very simple differential equation because, I mean, it's just d2 by dx2 plus d2 by dy2 plus d2 by dz2, right? That acting on some function is equal to 0, right? That's a simple equation. In general, you can have complicated functions of x, y, z multiplying these different terms. No? In that case, it's very I mean, there's no easy way of getting the Green's function even. No, UP is a particular solution. The general solution is this. Because if I have two solutions, UP and UP prime, then the difference between these two is a homogeneous solution. It's also a homogeneous differential equation, right? And for homogeneous, we already know the most general is U1 and U2, right? I mean, a linear combination of U1 and U2. Yeah, that is the good point. I should have mentioned that. So difference between any two solutions of this equation is a solution of the homogeneous equation, right? Okay, so let's discuss the Green's function idea. Okay, so in this chapter we'll be concerned also about the boundary conditions. I mean, here in this so far discussion there was no there was no choice of boundary condition, right? But now for the Green's function we need to specify the boundary condition. In fact, the main very intuitively, what is the Green's function idea? I mean, suppose I'm given some differential operator. And I will call it Lx. I'll just explain what. So Lx is some differential operator, which okay, in general, some nth order differential operator. Differential equation will be some an dn by dxn plus a, and these are coefficients. These themselves can be functions of x, right? They could be functions of x, dn minus 1, dxn minus 1, plus so on and so forth, all the way up to a1 d by dx plus a naught, right? So all these coefficients are in general functions of x. So this is an nth order differential operator, right? And in general, when you look for differential equation, solution of differential equation, essentially the equation is something of this type. For the homogeneous case, and if it's inhomogeneous case, it will be this will be not zero, right? So this is the kind of equations you're looking at. So let's say inhomogeneous, so I put a Q here. Okay. This is the kind of differential equations we are talking about, right? Now, this very much looks like, okay, I have an operator here acting on something, gives you something, right? So if I could somehow find the inverse of this operator, right, then I could just suppose Lx inverse. I have an Lx inverse existing. That's the point. This is in a formal way, in a very formal way. I'm just trying to give you an intuitive argument, understanding of Green's function. Then you see I can multiply both sides by Lx inverse, and you see you can find u equal to Lx inverse q. Okay. If you could find Lx inverse. Right? So actually the Green's function is this, in fact. This will be the Green's function. Okay. But for Lx inverse to exist, there must be no zero eigenvalue, right? You remember that from the matrix, for the first chapter, when we discuss if you have a matrix, say, take even a Hermitian matrix, and for the matrix inverse to exist, you must have no zero eigenvalue, right? Because if the zero eigenvalue is there, determinant of that matrix is 0, because determinant is always a product of eigenvalues. Okay? So determinant is 0, and the inverse will not exist. So for this to exist, there should be no zero mode. There's no zero eigen mode, or no zero eigen mode. But on the other hand, when we solve the homogeneous equation, that's exactly the zero mode, right? So So what will happen is that, as I said, we are guaranteed, although I have not proven to you, but we are, because I have not proven to you because I have not constructed U1, right? If I could construct U1, then I have proven to you there are two independent solutions, which are zero modes, because with the right hand side equal to 0, right? I mean, generally the eigenmode problem will be Lx u equal to some lambda u, where lambda is eigenvalue, right? And u is the corresponding eigenfunction, right? So in particular, if lambda is 0, right hand side is 0. So, and that is what we call homogeneous solutions to the homogeneous equation, right? So we know that for a second order differential equation there are two linear independent solutions, right? But then of course this will not exist, right? But I also told you that those a general solution will be a linear combination of those two solutions, right? And those two coefficients I have to determine by using boundary conditions. So now suppose there was I have chosen boundary conditions such that there is no, I mean, no C1 and C2 exists. I mean, there is no solution. Okay. In that case, there will be no zero mode. Okay. And then I can talk about the inverse. So in this discussion, the boundary conditions will play an important role. Okay. So far, it didn't play a role, but now it will play a role. Okay. So this is the main idea. So I have to just make some. Today, I think I'll just start with some basic definitions. So what we will do is that, so this is acting on some function u, on some functions u. So we will call always this such kind of an expression as a formal expression, okay? Because when I write such an expression, I'm not specifying any conditions on what kinds of functions it should act on, meaning no boundary conditions have been specified, right? But when I use the notation that we are familiar with, this kind of notation, okay, this kind of notation, there's a vector space where this operator L acts, right? So when I use this definition, when I use this notation, I will mean that this is a vector space, which are basically a space of functions, right? A vector space of functions, but those functions will come with certain suitable boundary conditions. Okay, that's what. So, but I mean, so basically this means the same. Lx acting on u, this differential operator acting on u, but that u is not an arbitrary function. It's subject to some boundary condition. So that's all. So it's just this different notation. This notation means the boundary condition is specified. Here it means there is no specification of boundary conditions. That's all. Okay. So I mean, so given this, I mean, let's. Okay, here it was nth order differential operator, but let me go back to the second order. Okay. So this is, although this analysis you can do for arbitrary. I mean, all these things that I'm going to talk about is formal definition. You can do it for arbitrary nth order differential operator, but we'll be only just stay with the second order differential operator. In fact, I will again use this symbol A, B, C rather than carrying the subscripts around. Yeah, I think I'll just use A, B, C. Otherwise, I'll have to keep track of the subscripts A, B, and C. Now, we already, remember we discussed about the boundary conditions. We said for a second order differential operator, you need two boundary conditions, right? You can choose in different ways this boundary condition. Yeah. Either you choose say the value of the function and the first derivative of the function, value of the first derivative of the function at one point, or you can, but altogether you need two data, right? That's the thing. So, so the boundary conditions we already mentioned before are involved basically two types of, I mean, in terms of, suppose I'm talking about x is in some interval, a to b. I shouldn't use a, b here now. No, I don't know, what shall I call? x0 to x1. x0 to x1. This is my interval, not to use this a, b in this notation. Yeah. These are all functions of x, yeah. Okay. So this is my interval. So generally the boundary conditions which also appears in physics, the boundary conditions will involve say the values of the functions at these points, endpoints, and the values of the first derivatives of the endpoints, right? So the two data could involve something like alpha u at x naught plus beta u du by dx at x naught plus similar quantity, I don't know, gamma. I think last time I used this notation, right? Delta du by dx at x1. That could be one, I mean that could be 0, for example, and another could be with another combination. I don't know, I was using alpha prime, I'm not sure. Alpha prime ux naught plus beta prime, etc. All the things replaced by primes. Okay, but those two conditions must be linearly independent. They should not be. It should not be that one condition is just some number times another condition. Right? Otherwise, you don't have two independent conditions. So the same equation with alpha, beta, gamma, delta replaced by primes. Okay. So these are the type of conditions we have. Okay. So first of all, in talking about such things, when we use a symbol, you have a notion of. First of all, there's a vector space here, so you also have the notion of inner product, right? Some u and v, there are two vector spaces, and this will be given by some dx, some weight function. There could be some weight function, and v bar complex conjugate ux, okay, from x naught to x1. This inner product satisfies the definitions of the inner product. I mean, all the conditions of the inner product, right? Linear in this vector, antilinear in the other vector, right? All the properties is satisfying. Then the natural question is there a definition of adjoint operator, right? I mean, we have seen that in the finite dimensional cases. So what will be the adjoint operator? So for that we have to use this again, this definition VL dagger, say u. That should be equal to u L V complex conjugate, right? So we need to somehow get this concept, get this, I mean, the candidates for what do we mean by adjoint operators and so on. So what is the difference here? I mean, here, say L was acting on this vector, here the L dagger is acting on that vector, right? Okay. So suppose I try to write something like this. So I have L acting on u, v. Well, L acting on u, we said is this differential operator acting on u. So that is the same as Lx. When I say this Lx, meaning this differential operator acting on u, where u is given, the function is given to you. And then I multiply by v bar, then multiply by the weight function, and integrate dx. Right? That's what this will be. Whereas if you try to look at something I mean, L dagger acting on v and u, well, what will that be? It will be again dx u bar, and let me take the complex conjugate of that. Okay, so u bar, then you have some L dagger, which we still have not defined how we have not specified what L dagger is. But if L dagger existed, you would have something like this L dagger acting on this function v of x, right? And then I would take the complex conjugate of the whole thing. L dagger acting on v, right? So how will I mean, I am given this Lx, which means this operator is specified, a, b, c functions are specified. How will I construct? Sorry, there's a weight function I forgot. Okay, how will I construct L dagger? Answer actually is almost obvious, right? I mean, essentially, from something acting on u, something operating on u, I want it to operate on v, right? So what is to be done? Well, this is a differential operator, so I can start doing integration by parts, right? So that is the idea. So we start doing integration by parts. But when we do the integration by parts, there will be always boundary terms. Okay. So what we will do finally is that we will choose so suppose I am given that the u satisfies these two linearly independent boundary conditions. Okay. Then when we do this partial integrations, integration by part, by the way, the origin of the partial integration, I mean this book is using continuously partial integration incidentally. So maybe both the terminologies exist, right? Integration by parts and partial integration, I don't know. So when I do this, I'll get this boundary terms, okay? Then what we'll do is, if possible, we will impose some boundary conditions in the V. I mean, we will also satisfy two independent boundary conditions, right? But we'll try to choose the boundary condition in such a way on V such that all the boundary terms disappear, okay? Because otherwise, we cannot get the L dagger. There will be all these boundary terms floating around, right? So that will be the strategy. And fortunately, it will turn out that it will be possible to find a boundary conditions on V such that these boundary terms all cancel.
It seems like you're looking for a Hermitian operator.
Yeah, I mean at the moment, of course, just adjoint. But if the operator, if the L dagger as a differential operator, I mean L dagger will also be some differential, second order differential operator, obviously, right? Because when I do integration by parts, what if it's a second order you started with, you'll end up with also a second order operator on V, right? Okay, but this A, B, C may be different for that in general. When you do this integration by parts, it may not be the same, right?
If we impose boundary conditions like that, the integrand of those boundaries to vanish, then
Yeah, so there are two things. Apart from the, okay, so let me come to that. Let me actually explicitly work it out. Then you'll see that expression for L dagger will not be in general the same as L. No? That's a problem apart from the boundary condition problem. So even if you have managed to get rid of the boundary terms, right? Even then, the form of the L dagger will not be the same as L in general. Only for special cases it will be. So this is the LX. So let's just plug that in here, and let's start doing integration by parts. So I'll explicitly let's write down. So what is it? V L U. This is equal to x naught to x1 dx v bar w v bar, and then you have a d2 by dx2 plus b d by dx plus c, okay, u. That's what it is, right? Now I start doing integration by part. So let's first do the first. This is as it is. There's no differentiation here. So this will stay as it is. Here, when I do integration by part, so I will get a boundary term, which will be. Let's keep also the boundary term. That will be from here. It will be simply w v bar b times u, right? Integral. I mean, okay, x1 to x0. That will be the boundary term coming from there. Then there will be and then what will be left over? So maybe I should write here. So here I'll put all the boundary terms. So then, so here you get minus. You see, when you do integration by part, I get a minus sign first of all, and it's going to act on everything here. B w v bar. So you'll get here d by dx acting on b w v bar times u. U is there now. So that's integral dx x naught to x1. Now let's do. In fact, there is also plus CV. CV is minus CV, right? Okay, C is as it is. So plus the integral dx w v bar c u x naught to x1. Because for that I didn't have to do anything. Now I do the here first one integration by part, right? So then I will get a boundary term which will be plus w v bar a du by dx, because I still have one du by dx, right? So that's again the boundary term. And then I will get, so let me write here, from the other term will be minus dx d by dx acting on w v bar a times du by dx, correct? Yeah. But this is still not good enough. I mean, there's still differential operator. So I need to do again an integration by part. So that time I will get a boundary term, which will be minus d by dx acting on w v bar a times u, right? I mean, d by dx is only acting there, not on the u, x1 to x0. And then the other term would be simply d by dx acting here with this flip of the sign, right? So it will become plus d2 by dx2, and then here you just get u. Okay. So now we are more or less in the form that we wanted. So nothing is acting on u, everything is acting on v bar, right? And these are the boundary terms. So let's just call this whole thing, let's just give it a name to all these things. This is, I call q, let me use the same symbol, q u v, q of u v bar, that is this whole thing. But let's look at the I mean, this is the boundary term, and that is the bulk term. I mean, that's to be integrated, right? So let's focus on that first of all. We'll worry about the boundary term, maybe not today, maybe tomorrow. We will show that there are boundary conditions which can be using which you can make this to vanish. But let's first focus on that. So that part is, so the conclusion is so far that we have VLU is equal to this boundary term q u v bar plus what we have here is dx x0 to x1 and okay, this u w times u, okay, and then what is inside here is this operator which is 1 over w, because I multiply and divide by w, right? W I want to take out because that's the way part of the definition of the scalar product, inner product. So 1 over w, and then you have d2 by dx2. If you want to write it as a, I mean, you can open this bracket also, right? Maybe better to open the bracket. So one term will be when the both derivatives act on the v bar. Okay, so there the w will cancel because no derivatives acting here, and you're just left with a d2 by dx2. Okay, I will put all of these things outside v bar. So there is that. Then there will be a term where one derivative hits v bar and other derivative hits the product of wa. So, but there are two ways of doing it, right? So there will be a factor of 2, and then you get here 1 over w d by dx, d of acting on wa divided by dx, I mean derivative of wa times d by dx acting on v bar. Okay. But then there is also another d by dx acting on v bar, which is coming from here, right? And that is coming with a minus sign. So the overall coefficient with the derivative operator is minus b, and this w when I divide it just cancels. This w is there, right? So it's just minus b. This whole thing is coming with the first derivative acting on v bar. And then there are some constant pieces, I mean some meaning not non-derivative pieces. So that is when both derivatives hit wa. So that's one piece which is, so there is a 1 over w d2 by dx2 acting on wa. Okay, that's from there. Then from here the derivative acting here, so it's a minus 1 over w d by dx acting on bw, and then plus c. Right? All of this is acting on v bar. So now you see, okay, it's true the second derivative has again the same coefficient a, but the first derivative has this coefficient. First of all, the b has flipped the sign to minus, and then there is extra pieces, right? And then this constant piece has a lot of pieces, c plus all these things. So in general, this is what you would call L dagger. Actually not exactly L dagger. What is this supposed to be? This whole thing, I can erase all this part, no? Because everything I put together. I mean, there's all this part I put together there. Okay. So I erase this. This boundary term, okay, leave it as it is. This whole thing, suppose that I could get rid of this. Suppose I could get rid of this boundary term. Then I would call this as U L dagger V complex, the whole thing complex conjugate, right? So so this must be, so so this thing without complex conjugate would be simply complex conjugate of that, right? When I take the complex conjugate of that, so this implies, okay, let me write down. So U L dagger V should be therefore just the complex conjugate of this, which is so I'm assuming that you can make Q to vanish, assuming Q be equal to 0. This is all assuming that. Then this would be complex conjugate of that, which is W being the weight function is real, is positive, in fact, even weight function is positive. So you get here x0 to x1 dx. So W is real, so complex conjugate is the same. Then you get a U bar complex conjugate, and from here you get A bar d2 by dx2, because A could be complex function, right? I mean, A is a function of x. X is real, but it may have complex coefficients, no? Complex d2 by dx2 plus 2 over W. W is real, d by dx of W A bar minus B bar d by dx. And then finally, you have all these things, C bar minus 1 over W d by dx WB bar, and then plus 1 over W WA bar. So lots of terms. All of this acting on V. So we will call this as L dagger. L dagger is a formal differential operator. So we would call this whole thing as L dagger X. Okay, so now let me say why I can make this to vanish. Okay, I mean I can choose some suitable boundary boundary conditions on U are given to you, right? Because that is the original vector space where this Lx is acting. So there I'm already assuming that that vector space has been defined, which means the two linearly independent boundary conditions have been given for the U's, right? But then using these two linearly independent boundary conditions, I can, for example, determine there are four quantities here: U at x0, U at x1, du by dx at x0, and du by dx at x1. Alpha, beta, gamma, delta are some fixed numbers that those numbers are specifying what your vector space is, right? So once I give you these numbers, alpha, beta, gamma, delta, and similarly alpha prime, beta prime, gamma prime, delta prime, I can determine two of these four quantities in terms of the other two quantities, right? I mean, I have two equations and four unknowns, right? And I said they are linearly independent, right? So therefore, I can determine two in terms of the other two, right? So you plug that back here. So you see, there are, again, look at this here. What is appearing here? The value of U at x1 and x0, and the value of du by dx at x1 and x0, and similarly the value of U at x1 and x0, right? So once so just to take an example, suppose I can use these equations to determine the derivatives of the U at x0 and x1 in terms of the value of U at x0 and x1. Suppose this alpha, beta, gamma, delta are such that you can do it. It's not always, I mean, that depends on the choices. But for all choices, it's true that two of them can be determined in terms of other two, right? But just to be simple, let's suppose that these two I can determine in terms of U at x0 and U at x1. So this I can substitute by U at x0 and U at x1, right? So then everything here can be written as U at x0 times something plus U at x1 times something, because it's linear in this U and derivative of U, right? So this whole expression, I can write it as u of at x0 times something plus u at x1 times something. But now look at each of these terms, coefficients. The coefficient of u at x0 can involve what things? Can involve the value of v and the value of the derivative of v at the two endpoints again, right? So now demand that independently these two quantities are 0, the coefficient of u at x0 and the coefficient of u at x1. Each of those coefficients is linear in v and derivative of v at the two endpoints. So if you demand that, you get two boundary conditions on the v, you see. So if you choose those boundary conditions for v, then this q vanishes. So this is the idea here. Just to give an example, suppose my conditions were let's say Dirichlet boundary conditions, okay, for the initial space, Dirichlet boundary condition. So I mean just to show that this is possible. Suppose I choose Dirichlet boundary condition, or let's say even Neumann boundary condition. What is the Neumann boundary condition? It is simply du by dx at x0 equal to du is 0 and du by dx at x1 equal to 0. Very simple Neumann boundary condition. I mean, so that just corresponds to, for example, choosing in the first equation choose alpha equal to gamma equal to delta equal to 0, and the second equation you choose alpha prime equal to beta prime equal to gamma prime equal to 0, right? Okay, so from here in this, when you look at here, this term drops out because this is all derivatives at the x1 and x0, right? So what is left over here? So this q becomes q of u and v bar becomes w b v bar, all of this evaluated at x1 times u at x1 minus w. Actually, I can combine everything, right? So this is, let's see what multiplies u at x1. U at x1, there is a one term from here and one term from there. So that is this minus d by dx acting on w v bar a at x1, evaluated at x1, right? All that is multiplying u at x1. And similarly, minus the same thing at x0 at x0 minus d by dx w v bar a at x0 x0, yeah. This whole thing multiplying u at x0. That is what this q became for this Neumann boundary condition. Okay. Now Neumann boundary condition is only telling you the first derivatives are vanishing, but it doesn't fix at all the value of u at x1 and u at x0. Those are completely free, right? So the only way this can be 0 is if each of these terms are 0, right? But that gives you again a boundary condition for v bar and dv bar by dx, right? In fact, you can see that, okay, you get two terms. One, when the derivative hits wa, so that is again coming with a v bar, and another term and derivative hits v bar, right? So it's a combination of the value of v and the value of the dv by dx at x1 and x0. So they have to be 0, and that gives you the boundary conditions for the v. So you say that, so if I restrict my the what appears here, this is called the dual vector space. Okay. Remember in the inner product you have the vector space, and the other side is the dual vector space. So the boundary conditions of the dual vector space, you see already in this example, is not necessarily the same as the boundary conditions on the initial vector space. Initial vector space I just chose Neumann, but here it's not Neumann. It's a combination of the Neumann and, I mean, it involves both the value of the field, the function, and the value of the first derivative of the function. It's a combination of them which has to vanish. So both the things, not only that L dagger is very different even as an abstract operator, is very different from the original L, but also the boundary conditions are different on the U space and the V space. So L is going to act on the original vector space, and L dagger is going to act on this different vector space specified by these boundary conditions. Okay? And once you do that, then the the Q vanishes, and then this really becomes you can call this as an adjoint operator. Yeah, maybe I think I'll stop and then continue from here.